there are some interesting consequences of the definition of angular momentum. We have already seen one in the previous video. The angular momentum is an origin-dependent quantity. But let's take a look at a couple of others. Because the cross product is zero, if the two vectors are parallel to each other, parallel or anti-parallel, they just have the same direction to them. That means if a particle is moving radially to or away from the origin about which it is rotating, so that is directly towards or away from the origin about which it is rotating, then the angular momentum will be zero. See the following scenario. I have a particle moving directly towards the origin. Its r vector is as follows. As you can see, r and v are parallel, or technically anti-parallel. So when you take the cross product of these vectors, you will get zero. Remembering, of course, that v will be in the same direction as p, the linear momentum, since p is just mass times velocity. This means then that the angular momentum is zero for this particle moving directly towards the origin. And as you can see, the same thing would result if it was moving directly away from the origin. So we call this direction the radial direction. And hence, if a particle moves radially to or away from the origin, the reference point about which you are calculating the angular momentum, then the angular momentum is zero. This also means then that the angular momentum is zero if a particle moves along an axis of rotation that passes through the origin. Suppose we have an axis of rotation like this, so it's coming out of the page and into the page. If we have a particle rotating about this axis of rotation, it would look like this. And at a moment in time, its p vector would look like that. However, if the particle was on the axis of rotation and just moving along it, so out of or into the page along the positive z or minus z direction, if we make the z-axis to come out of the page and into the page, then it is moving directly towards or away from the origin, and therefore its angular momentum is zero. Just like if the particle was moving directly towards the origin in the xy plane, as we saw in our previous example. For the same reason, the position vector and momentum vector are parallel to each other in those cases. We therefore reach the following conclusion. The angular momentum will be equal to zero if you calculate the angular momentum about a point that is along the particle's straight line motion. Meanwhile, the angular momentum will not be zero relative to any other point. So if we want a non-zero angular momentum, we have to choose a point that is not along the particle's straight line motion. What this also means then is the rather strange conclusion that a particle moving in a straight line has angular momentum, so long as you calculate the angular momentum relative to a point that is not along its motion. We could have seen this from the definition straightforwardly as well. We have r cross p. P is just a linear motion quantity, so if an object is moving, if it has velocity, it will have p. It has linear momentum. R is just the position vector. It's the vector from the origin to the particle's position. The position vector can exist even if the particle is just moving in a straight line. So a particle does not have to rotate to have angular momentum. Let's see an example. Suppose we have a particle traveling parallel to the x-axis as follows, where we will take the positive z-axis to be coming out of the page. In this case, we can draw a position vector. We can draw a vector from the origin to the particle, where we take the origin of the coordinate system to be the point about which we will be calculating the angular momentum. The r and p vector, they are not parallel to each other, so their cross product will be non-zero. Our particle will have angular momentum. If I continue drawing my p vector out, you'll see that the perpendicular part of r is as follows. And so the magnitude of angular momentum is, based on one of our methods for calculating the magnitude of angular momentum. And as you can see, it is non-zero. R has a perpendicular component to p, or we could do it the other way, that would be a little bit more difficult. P has a perpendicular component to r, and therefore the magnitude of angular momentum is non-zero. This particle has angular momentum about this origin. And if you're interested in the direction, then you can use the right-hand rule, and you will see that the angular momentum is going into the page. Slide your p vector over so that way its tail is touching the tail of the r vector. Then do the right-hand rule, hands in direction of r, curl towards p in the direction of the smaller angle, and you'll see your thumb sticks into the page. So we can write the full angular momentum vector as follows, or like that, pointing in the minus k hat direction along the minus z axis in the negative z direction. Keep this in mind. It will be useful for solving problems later, as we will see in some examples in later videos.